All right. So last lecture we talked about scientific measurements and some of the properties of scientific measurements as far as the resolution of an instrument or the physics of an instrument. We also discussed how you don't always need fancy equipment to measure and determine some very profound results. So this time we'll talk about sort of the philosophy of science and the scientific attitude. So in high school, the whole scientific method is just drilled into your head. In particular, if you took AP European history, there's a whole thing about like Descartes and Bacon and all those that were developing the scientific method. Even in introductory like biology or physical science, uh, they have sort of this cookie cutter way to approach science, and that's not necessarily the case when you get out into the real world and you're interacting with real scientists. There is no one scientific method, even though we've all sort of been taught to believe that. Um, so the modern scientist works upward, essentially starting with facts that are proven, or at least that we're very confident in, using these facts as stepping stones to make more generalized inferences about the world. So, some common features of scientific methods, no matter which one you're using, some of these features are the same, and that would be that there's recognition of a question or a puzzle or something that seems to happen, but no one really knows why that happens. Okay, so you can think of it as like some unexplained fact. Now, in this fact, um, there may be enough information to actually form a hypothesis or essentially a guess. Okay, so we'd want to essentially guess at what's going on, and this guess might help us solve the puzzle. Okay, so we're going to work backwards. We have a puzzle. Okay, we have a hypothesis about that, about the puzzle. Um, and then we have to come up with a prediction. So if we hypothesize about how this puzzle works, or we hypothesize about the thing causing the puzzle, then we need to make a prediction. Well, if our hypothesis is true, then what? Okay, so assuming that our hypothesis is true, we have to think about the implications of that. Okay, so if we hypothesize that there's, a tiny elf living in our refrigerators that turns off the light when we close the door, well, the implication of our hypothesis is that, well, he's gonna eat something. So maybe there's evidence of, I don't know, Snickers wrappers lying around in the refrigerator. And that's our evidence of the little elf turning the light off. Okay, so that's our prediction. Granted, that's not a very good one. That could be our prediction of our hypothesis of the puzzle of the light in the refrigerator. Does it actually go off when you close the door? Okay, well, we can start performing experiments or gathering evidence, maybe even making calculations to test this prediction. Okay, if we predict that there's candy wrappers from the elf in the refrigerator, then we can perform experiments. We can look for that evidence. Okay, once we collect our evidence, granted, the example I'm using is not a good one, but when you more carefully think this out, what you want to do is you want to synthesize all of these pieces into a general rule. So you want to take your hypothesis, your prediction, your experimental findings, and then formulate that into a statement that you can write down that solves the puzzle. So if this was our puzzle, how does the light work in the refrigerator? Maybe a better hypothesis would be to go ahead and say, well, maybe there's a sensor that turns it off. Okay, well, there's our prediction. That would imply the existence of a sensor. And then for an experiment, we could put a camera or a video camera in the refrigerator and close the door. We can listen for clicking sounds of the mechanics of the switch, right? And then once we collect all that, we can synthesize those results and actually make a rule or a statement that refrigerator lights turn off when the door closes because of an internal switch. I know these are stupid examples, but it gets the point across. So these steps are reflective of a scientific attitude. Okay, so this is the attitude that hopefully, but not always, shows up and is common among scientists. And it does entail a willingness to admit error, because if we have no evidence to back up a hypothesis, we have to abandon that hypothesis. So with this scientific attitude, there's usually four pieces of information that we work with when we go through this process. So we have a hypothesis, we have facts, we have laws, and we have theories. So in regards to a hypothesis, this is essentially just an educated guess about how something works. It's, like we said on the previous slide, it's a guess about how this unsolved puzzle works, this puzzle being some piece of the universe. And we, essentially with a hypothesis, you assume it's factual until it's tested, right? You say, okay, this is true, but as soon as it's proven wrong, you have to abandon it. Okay, well, a fact in science is close agreement by competent observers. I don't really like this definition of fact because it makes it sound like as long as everyone agrees, then it's true. But you could think about this in terms of like a close agreement by, you can get rid of this and say experiments. So that sort of takes the human element out of it and says, okay, if all these experiments always agree, then this is probably factually correct. Now, for a fact or a theory to become a law, you have to repeatedly test it, and there can be no contradiction in the evidence whatsoever. If maybe some of it is true, but parts of it are not true, then that's different. But when everything gets so solidified through repeated testing, that becomes a scientific law. And then a theory is, most people use the word theory as like a guess or just a harebrained idea. Okay, but in this situation, in the sciences, a theory is not the same thing as a guess. Okay, if we want to guess, we're going to come up with a hypothesis. So a theory is essentially a large body of knowledge that we put together to get some big ideas out of it. So if we have 100 scientists working on, I don't know, different aspects of black holes and how they work, the idea with the theory is you'll get all those different pieces, synthesize them together, and then come up with a list of simple facts about black holes. That's the working theory of black holes. So, of course, this large body of knowledge needs to encompass well-tested and verified hypotheses, or at least well-constrained and well-calculated if you can't go there to do tests. And of course, this is about the natural world. So theories actually evolve as they go through stages of refinement. The general relativity that Albert Einstein came up with, that's been refined and added to over time. It's still the same theory, it's just, it evolves. This refinement process, this is very much a strength of science. So a lot of times you'll see newspaper articles that said, oh, this recent study says that coffee and caffeine is good for you. And then a few years later you see, oh, this recent study says caffeine and coffee are bad for you. The problem is with newspaper releases, they sort of oversimplify those findings. So maybe there's a study that says in this situation, coffee and caffeine is good for you. And then later on, there's another paper that says, oh, except for, a few, like maybe the elderly or really young kids should avoid it. Otherwise, it's good for you. There's nuances. And that's the idea of a theory, is where you get all these different pieces, all these nuances, and put them together into something generalized. But as an example, as far as refinement, you could think about the atomic theory of matter. So essentially, the whole idea of what atoms are and what they do, that's been around forever, like 400s BC, like third, fourth, fifth century BC. So we have like Democritus, who developed this ancient atomic theory and basically said whatever you're looking at, you can chop it up into smaller and smaller pieces until you can't chop it up anymore, and that is an atom. Okay, but then we move on to like the 1800s, where John Dalton did some work to actually use calculated pressures and vessels to determine the weights of atoms. Still not sure what they look like. And then you get to like J.J. Thomson's plum pudding model in 1904, where he said essentially an atom is this gelatinous blob, kind of like plum pudding, with electrons and neutrons and all these different pieces sort of floating around in it. And then, of course, we've had more improvements to this theory, this atomic theory of matter, until we get up to like Niels Bohr and the Bohr version of the atom, which that actually started incorporating quantum mechanics, and that's where we get the idea of like a nucleus with electrons around it. And that's the model that you'll remember from like high school science classes. But remember, that did start out with just some little sphere that you can't divide anymore. And then over time, we get up to this very accurate representation with the Bohr atom. So if there's science, we also have to talk about what is not science. Okay, and that's pseudoscience. Emphasis on pseudo, which pretty much means fake or not true. So in science, a hypothesis must be testable. Okay, this is very important. Whatever you say, whatever hypothesis you come up with, there has to be a way to test it. Which means there must be a way that it could be proven wrong. So that doesn't mean that eventually it will be proven wrong. It's just got to be possible to be proven wrong. So if there is no potential test for wrongness, then a hypothesis is not scientific. Okay, so if I wanted to say that, I don't know, behind the sun there is an invisible unicorn, well, we don't really have any probes that can whip around and get there close, so, we might say that I'm relying on the fact that we can't really go there to measure this, or maybe I could even say inside the sun there's invisible unicorns. Well, we can't send a probe into the sun because the probe burns up. So that's an example of there's really no way to test for that, so it's not really a scientific hypothesis. On the other hand, if we make a hypothesis and we can test it and it's confirmed, we can then use that as a stepping stone to more discoveries. So let's think about this example that's less ridiculous than some of the examples I've been using. So which of these are scientific hypotheses? So we have one, atoms are the smallest particles of matter that exist. The next one, B, we have space is permeated with an essence that is undetectable. Or C, Albert Einstein was the greatest physicist of all time. So let's start at the bottom and work our way up. Let's start with C. So if we wanted to test to see if Albert Einstein was the greatest physicist of all time, well, first we need to ask, well, what's the definition of a physicist? Is it someone that's teaching at a university or working in a national lab? Or maybe it's just someone that knows a lot about physics. Well, if it's the case that it's someone that knows a lot about physics, well, that could be anybody. That could be like, a 12-year-old living in India that's like brilliant, but doesn't really like show off or get any publicity from their work or their ideas. So really the kid in India might be the greatest physicist of all time, but nobody knows them. So that's not really easy to test. It's not there's no experiment really to objectively deal with that. So I'm going to say not that one. B, well, this says space is permeated with an essence that is undetectable. So apparently, according to this, there's some weird field or essence that's floating around. But if it's undetectable, we could never do anything to measure it. So the whole point of this is this undetectability. We could never design an experiment to find it. Well, that in the definition of the hypothesis itself says it's not scientific because there's no way to actually do it. Okay, so this one, A, actually makes sense. Atoms are the smallest particles of matter that exist. Okay, so is this testable? Well, yeah, it is. There is a test for falseness, and that would be a particle accelerator. So CERN, I think my window might be over this logo, but nonetheless, you can look at the lecture notes. So CERN is actually an atom smasher. It can smash particles together, and it breaks them apart into smaller particles. It's the world's biggest particle accelerator for now. So there's a test, there's an experiment, there's a mechanism that would let us smash atoms together and show that they fly apart into even smaller particles. So statement A is scientific because there is a test for falseness. Turns out A is false. Okay, so in summary, science is the body of knowledge that describes order within the universe, and it's an ongoing process. So remember, this evolves over time. It's an ongoing process of organizing knowledge into testable, that's very important, testable laws and theories. Okay, so now we've talked about the righteousness of science and scientists. Let's talk about some of the misconceptions and deceptions that are out there. So, as with everything, sooner or later, mistakes are made, deception is discovered, and wishful thinking is exposed. So, generally, the penalty for fraud is professional communication, and this is in the science community. In the science community. So if you are ever caught lying as a scientist and you've tried to publish fake research, pretty much you will lose your job and you will never be employed as a scientist anywhere again. That's how the process should work. Generally, it does. So one example we could talk about is the whole idea of vaccines cause autism. A lot of people have heard that, whether they believe it or not. A lot of people have heard that, but no one really knows where that claim comes from. So let's explore that as far as like deception and misconceptions. Okay, so where this come from is in 1998, this doctor, a medical doctor, his name was Andrew Wakefield, and his colleagues, they published a paper in a scientific journal. It's a medical journal called The Lancet. And they hypothesized that the MMR vaccine ultimately caused autism. Well, when he claimed this in his paper, in his experiments that he put together to show this, he only included 12 children in his study. I guess I should point out that this statement was it caused autism in children. Okay, but he only used 12 children in his study, and 8 of them were diagnosed within 1 month of receiving the MMR vaccine. So that, in and of itself, that sounds alarming. Wow, there's these 12 kids, and within a month, they were all diagnosed, or 8 of them were diagnosed with autism. But there was some issues. So 12 is a really small sample size. When you consider the population of the Earth right now is like 6 billion, and you're going to make an assumption or form a hypothesis off of what happens in a group of 12, that's a really small sample size. And the MMR vaccine is typically administered right around the time you would be diagnosed with autism. So he's got these two things that could be completely unrelated, but because they happen around the same time, he's putting this idea together that they're correlated. I mean, there's actually a correlation, and this is true. There's a correlation between ice cream sales and people drowning at the beach. The more ice cream sales there are, the more people drown at the beach. That does not mean ice cream sales or the selling of ice cream causes people to drown. That just means on hotter days, more people buy ice cream and more people go swimming. Okay, this could totally be one of those situations, but Andrew Wakefield is sort of forcing this correlation. One big thing he did is he didn't have two groups. He didn't have a control group. So there was no control group. And essentially with a control group, you just wanted a separate group to compare to. So 12 kids that were not vaccinated. Okay, you have these 12 kids that were not vaccinated, 12 that were, and then you watch and see if the rates of autism changed between them. Okay, because if the rates were the same, well, then it wasn't the vaccine. But he didn't consider a control group at all. So this paper was eventually retracted. Actually, recently, it stayed in publication for a while, which was shocking. And then there's been, I don't have the fact here on the slide, but I think there's been 25 more studies using huge sample sizes, thousands of kids. And these big studies, they can't show a link. Okay, so it's just this one little anomalous paper that was published, and look at what happened. Everybody's heard the vaccines cause autism, and that literally came from one paper that got out there and stayed for a little too long. So if you're thinking about your own ideas about a topic and whether you're wrong or right, this is something that the book discusses. But a good personal test for misconceptions is to see how well you can articulate opposing ideas around your own thought. So if I have some idea in science, like maybe, I don't know, global warming is caused by just volcanoes. Well, I'm going to have a lot of critics that are going to come up with counterpoints. And the better I understand those counterpoints, chances are the better I understand my own point. And if I can really pinpoint what their critiques are and address them, chances are I'm correct. That does not mean I am correct, right? This is not this is not a test for your own correctness. But the better you can understand opposing critiques, the better you can articulate your own point. And the better you can articulate your own point, the more likely you are to be correct. So let's sum up what is pseudoscience, since we've been talking about deception and misconceptions. So like we've already talked about, for a claim to be scientific, it must be reproducible. There has to be a way to get those results every time where someone else can validate what you're doing. And then once you collect the data from those experiments, it's got to be open. You got to share those results so other people can see it and also critique your work. So claims that do not meet these standards, well, that's called pseudoscience. And some pseudoscientists, they don't even realize that what they're doing is pseudoscience. There's a case here in California where you could actually get a doctorate degree in homeopathy, which is basically trying to, this is an oversimplification, but basically you're trying to use essential oils to cure chronic diseases and do things like cure cancer. People graduate with this degree, they go out and practice in the medical field. If you're interested, you can send me an email, but there's an entire podcast this woman does where she actually got this doctorate and then realized it was craziness and actually left the field completely, and the podcast is about her experience in it. So there are some pseudoscientists you got to watch out because they don't know what they're doing is actually pseudoscience. And then there's other people like Andrew Wakefield who are just knowingly deceptive and refuse to really acknowledge what the data actually says. So the results of rampant pseudoscience is obvious. There's actually been several instances where scientific literacy tests have been given to the public that show most Americans actually lack an understanding of basic scientific concepts. There's some crazy thoughts out there. Okay, so we've hit science, we've hit pseudoscience. Now let's sort of branch out from the sciences completely and start talking about art and religion. Like, where do these two things fall into the grand scheme of what we're talking about? So in this case, science is about discovering and recording natural phenomena. Okay, well, art is about personal interpretation and expression. And then you can think of religion as just sort of trying to address the source and meaning of it all. So here's the way I like to think about it. So this here, this plot, this box, this is just from me. This isn't like some well-known approach to thinking about these. This is just my thought and how I like to present this. So in the bubble of humanity, which is the screen, in the bubble of humanity, what's inside the bubble, this is all we know, what's known, okay? What's outside the bubble, okay, what's out here is the unknown, things we don't know. So what happens, or at least the way I like to think about it, is art sits on the very edge of this bubble and lets us look back in and understand and express all we know. While science also lives on the edge, on this bubble, but science keeps pushing us further into the unknown. Science makes the bubble bigger, art helps us understand what's inside. And this whole process, I like to think of it as setting in the box of religion, because religion would be all-encompassing. Why does all of this happen? And again, that's just this entire box. It's just my personal view on it. Hewitt, the author of your textbook, actually has a really good quote. It says, "Unless one has a shallow understanding of either or both, there is no contradiction in being religious and being scientific in one's thinking." So there are some examples of mixing science and religion and making it go horribly wrong. One example being the flat earth. I'm sure you all have seen this popularized theory on TikTok or YouTube or something, but from their website, theflatearthsociety.org, their mission is to promote and initiate discussion of flat earth theory as well as archive flat earth literature. So their forums act as a venue to encourage free thinking and debate. So this whole idea of flat earth really started popping up in the early 1800s with this guy named Samuel Rowbotham, developed these views from a overly literal interpretation of the Bible. So if you're interested, the creation story in Genesis, if you go back to the original Hebrew, actually describes a flat earth with a dome on top, the firmament. And if you follow this link here, the three-story universe, there's actually a neat figure where someone has made a figure of what the original book of Genesis describes. And they walk through the original Hebrew, they walk through what it's been translated to, and they do a really good job showing that that's most likely how the book of Genesis was written. So this guy Samuel took this very hyper literal description of what the earth should look like and then tried to say, well, this is exactly what it is. Everyone else that's measured the earth is wrong. So do keep in mind that this was happening in the 1800s. Remember from our previous lecture, Eratosthenes, who measured the circumference of the Earth? Even Eratosthenes knew that the Earth was round in like the 6th century BC. So here we're in the late 1800s, and Samuel here is trying to argue against that. So there is a documentary. It's called Behind the Curve, I think. If you want to watch it, it's kind of comical, but I'm a little cynical. If you want to watch it, it basically is a camera crew that follows around some prominent flat earthers who do experiments to try to show that the Earth is flat, but they wind up showing that the Earth is round in the end. So, and at the end, they keep saying like, oh, well, the results look like this, but we need to refute it and come up with a different way. So they just keep coming up with different ways to try and show that the Earth is flat, and they keep showing that it's round. So this is not a scientific attitude. And there's a whole documentary about that if you'd like to watch it. The last thing is just a quick discussion of science and technology. So just so we don't confuse the two, science is concerned with gathering knowledge and organizing it. However, technology enables us to do that. We use the technology to gather the knowledge. We use the technology to organize it. So you can think of the technology as the instruments that scientists use to make this happen. So generally the technology comes out of science, but then goes back to help science and further science and knowledge. And something else to think about is all technologies have an associated risk. And when the benefits of a technological innovation outweigh its risk, then we accept it and adopt it. Kind of like cell phones. There's a risk of people using their cell phones while they're driving, and then they crash. But overall, the benefits vastly outweigh the risks. So cell phones have been widely adopted by lots of countries and cultures. But on the other side, if the risk outweighs the benefits, then this technology is not really used, or maybe it's used sparingly. So for example, x-rays, getting one x-ray like once a year, not going to matter. But if you get lots of x-rays, then your chances of cell damage in your body increases. That's why when you go to the dentist, the nurse will always wear a big lead vest, because the x-ray tech is always in there for multiple x-rays a day, so they're exposed a lot. That's why they need the lead vest. So in an x-ray machine, or getting an x-ray, is sort of an example of a risky technology that you want to use sparingly. All right, so just to sum everything up, at the end of my lectures, or at least at the end of course module, I'll have all these external links that I used. So if there's something that caught your eye and you want to read more about it, you can always go to the last slide and find the links to these things. You can also scroll back through and click on, not in the video, but if you download the lecture notes, you can scroll back through and click on a lot of these links. That'll take you to some extra information out there if you're curious. All right, so that's pretty much summed up the whole idea of measurements, science, and the scientific attitude. So next time we'll actually start talking about and doing physics.